What is this cobbled together mess, you might ask? Well, it's my latest project, and it's going to be tying into this current video that we're going to do. And you can see there's a bunch of wires and things going to it. And if we look at the oscilloscope, you can see we have absolutely nothing. And that's actually what it's supposed to be doing right now. Let me explain. So taking a look at my signal generator, you can see I have wires connected to both outputs right now, and they're both turned on. And if you look at this channel, it's 1 kilohertz, 500 millivolts RMS output. And if you look at this channel, it's the same, 1 kilohertz, 500 millivolts RMS. And by hitting the align phase button, it will make sure that both of these channels are tracking in phase with one another. So you have two identical sine waves, and when I feed them into this board, you get absolutely nothing out. Now, as you can see right there, absolutely nothing. Now, what would happen if we take channel 2 and make it a square wave instead of a sine wave? Well, you get a funny looking signal that looks like that. And if I take that square wave and turn it back into a sine wave, I get a sine wave. And that's because that is a function of my signal generator. Right now, what's happening is the two signals are out of phase with one another. If I hit align phase, like I showed you, now it disappears and you have nothing. So what's this all mean? So what you're seeing right here is a little circuit that I just built, and it's called a difference amplifier. Okay, and we call it a difference amplifier instead of a differential amplifier, even though this is a differential amplifier. But what we're concerned with right now is we're not trying to use negative feedback like in some of these diff pairs that you see in amplifiers. We actually are looking at the common signal, or we're looking at the difference between the two inputs. So if you look, you have, point with something, you have these two inputs and they each go into a buffer. All this is a buffer. So this is a one-to-one unity gain amplifier, and all its job is to take whatever impedance is here and switch it over to be able to drive a lower impedance here. It basically takes away the effect of whatever impedance signal you're connecting to it from this side here. But the real magic is happening in these two op amps, and this is your actual difference amplifier right here. If you see, we're going into the inverting and non-inverting inputs, and it's basically a unity gain system right now, the way it's set up. And what's going to happen is, since one signal gets inverted and the other does not, if you have two identical signals, phase, amplitude, frequency, everything, what's going to happen is they're going to cancel out, because this one's going to be inverted from this one, and when you sum those together, the sum total of a signal plus its inverted signal, inverted 180 degrees, is going to be 0. So you should get a flat line out of here. But if there's anything different, whether it's the phase, the amplitude, the frequency, wave shape, anything, that difference between these two channels is going to show up at the output here. And then this is another buffer amplifier, and it has variable gain. So right now I have it configured for unity gain, so it's not boosting anything. But what it's going to do once again is it's going to just drive this output, just act like a driver. And what I can do is, by varying this gain, I can make it up with this pot being in here, I can amplify the signal up to about 11 times. Yes, I have the amp that goes up to 11.
Yeah. The numbers all go to 11. Louder? Well, it's one louder, isn't it?
So anyway, the purpose of that is If we're looking at a very tiny signal, you can amplify it to make it easier to read on your scope, so your scope doesn't have so much noise on it and you're above the noise floor of your oscilloscope. You can also connect a spectrum analyzer, so if you want to look at a spectral analysis, like if you're looking at noise or something, you can do that. There is an offset null adjustment in here, or not offset, an input null adjustment. And the reason for that is if you're looking at two identical signals, like let's say we're comparing the left channel to the right channel of a preamp or an amplifier, but we don't quite have the balance control set perfectly, and there's a slight amplitude difference between them. This gives you a little bit of adjustment to be able to null that out. You don't really need this if you have a way of balancing these, but you just have to understand if the amplitude is slightly different between these, it's going to show up over here. So we just want to null out any differences in amplitude that we may have. And that's what that's there for. Very simple circuit, and then just a very simple linear power supply with some voltage regulators, basically, you know, an LM 7815 and 7915, and that's the whole circuit. So we're going to use that in this video to do some tests. Again, this was built at Booty Fab Labs, so it's not, you know, I didn't make a proper circuit board. I didn't want to, it probably would have been quicker for me to do a circuit board on KiCad and ship it out and have it printed than it was to try to do this on proto board like this, but I just wanted to work with what I had. This will be good enough for proof of concept, and if I really like this and you really like this, maybe we'll turn it into a little project that we can make some Gerber files and so forth and share them. But like I said, nothing in here this is not an invention. This is not anything new. These are things that have been around a really long time. And while I really didn't do much reading up on the life and times of Bob Carver, I think he did some similar thing to this when he was doing his transfer function modification. He called it TFM or whatever. And really, I think this is kind of the concept. Maybe he didn't use this. I mean, you can do this just with an oscilloscope by inverting one channel and using two channels on your scope. This is just kind of a cool way of doing it, and having, maybe we can add some features to this to make it a little easier to manipulate than by using just a scope and using your math, or inverting one channel and adding the two channels on an analog scope. You can do that, by the way. But yeah, just a simple circuit that's been around for a really long time that I just decided that we're going to play with it this time and just see how useful it is for us. Okay, so I have it all put together now because it works. And I did make one change to the schematic, and I'll update this and put it up on the screen before the video's over so you guys can screen capture it. But what I did was, instead of having the null, the offset null, which actually was pretty cool, I ended up just putting two separate potentiometers in here. So you can see the little X where I cut the wire there, and the wiper goes to each input, and then the input capacitor connects to one end of the pot, and then the other end of the pot goes to ground. And that allows me to adjust each channel individually. And the reason I decided to do that, I never really thought of this until after I had drawn this, and that is, what if we want to compare the input versus the output of an amplifier? So let's say I have a 1 volt RMS input, you know, for the input, and of course the output of the amplifier might be 20 or 30 or 40 volts RMS. So what I can do is I can balance that by turning this one up to allow the lower amplitude signal in here, and then turn this one down to balance it to this one, so I can balance it. So balancing will then require adjusting both pots. Now that's very sensitive. So you can see right now up here I have, well, you can't see because of all the reflections and lights and all that good stuff, but if you look up here, I have both channels turned on, and they're both set to the same thing, 1 kilohertz, 500 millivolts RMS, but they are not in phase with one another right now. One thing about this particular signal generator is if you just start up both channels at the same time, they will not be, the phase will not be aligned. You have to push that align phase button. So when you have both channels, so I have both channels of this 2-channel signal generator. When you first turn it on, the two signals will be out of phase with one another. It's just the way, it's a quirk of this signal generator. But if you hit this align phase button and you set everything the same, so they're both set to 1 kilohertz, 500 millivolts RMS, they will have an identical in-phase signal coming out of each channel. And I'm feeding those down into here. Let's get this down. Into the left and right inputs. And I have both pots turned up the whole way right now, so they're at maximum, input level. So there's no attenuation. And if you look on the scope at the output, there is actually a small offset. You can kind of see it in there right now. You can see how there's, basically it's because the channels are not balanced. And if I turn this on, and let me see if I can do a picture-in-picture thingy. And watch, if I turn this pot here, you can see they really get out of balance. And if I turn this pot, they really get out of balance. But watch as I rotate this very, very slowly. Watch what happens. It will drop, and then it'll start going up. Watch. See that dip? And then it goes up. So that's your null point. And watch, if I'm really careful how I do this, I can completely null that signal out. And it's kind of touchy around this camera, but you can see right there, now it's a flat line. And so that's how you null the signal out. Now, any difference between them, so let's say, let's go up here to the signal generator, and let's say I take channel 1 and I change it to a square wave. What happens? Well, first of all, we get a massive signal. And if I turn it down, you can see, no you can't. You can see what happens here. You get this funny looking waveform. If I turn it back to a sine wave, it goes flat. Now, also, if I go up here and see where it says phase, if I go to start phase for channel 1, let's change it to 20 degrees. Right there. And you can see now, down on the scope, that's the difference between the two signals. And now, no matter what you do, you cannot fix that. I can make it go higher by turning it down, but you can see you cannot null that out. Right about there's the null point. And if I adjust this, see how it nulls out a little bit? It dips and then goes back up. So that is the true difference between the two channels. So that's how you set these things up. I hope that makes a little bit of sense. You'll see more about how to use this when we actually test the two preamps. Now the same thing happens if you have different frequencies on each channel. So let's say one channel is 1 kilohertz, the other is 2 kilohertz. You see what happens? And this would be 3 kilohertz on one channel and 1 kilohertz on the other channel, and so forth. And you can see they kind of mix together. And that's the whole point of this thing. Align phase, and they disappear. So let's set this up and let's test some preamps with it. Okay, so here's our setup. And I did a little drawing so you get a better idea of what's going on, because this can be a little bit confusing right here. So we have the signal generator, and I'm just coming out of one of the channels with your basic 1 kilohertz sine wave. And I'm going into channel 1 of our difference amplifier, our little test jig here. I'm also coming out of a Y adapter and into the input of our preamp, our device under test. So essentially, this thing is monitoring what's going in to the preamp. I'm then coming out of the output of the preamp and into channel 2, which is this one right here. And that's also going from a Y adapter into channel 2 of the scope, so you can kind of see what's happening at the output of the preamp. Then we're looking at this output of the difference amp, and it's going to show the difference between the input and the output of our preamp. So this is all going to make a little more sense as we use it. So let's switch over to here. So right now I have a 1 kilohertz signal connected up. And I have the gain all the way down on this. And I have these two input attenuators set in such a way that the input and the output are, the two channels are nulled out against one another. Because remember, you have an amplified signal coming out. You have a lot more amplitude coming out than you have going in. It's about 10 times the amplitude, actually a little tiny bit more than that. And if you look at the oscilloscope, so here's channel 1 down here, here's channel 2. So this trace down here is the input, or I'm sorry, the output of the difference amplifier. And this channel right here, this trace here, is showing us the output of the preamp. Now, everything looks good right now. And again, I can adjust one of the knobs here. I don't know if I can show you here as I do this. Let's see. Hold on. And let's adjust the one channel to kind of null it out. See that? See how it kind of crosses through there? And I want to flatten that out as much as possible. And I'll turn that down even further so we can really get it centered. You can see how touchy it is now. And that's about it. So right there, this is showing just a tiny little bit of phase shift between the input of the preamp and the output. And that's normal. You should see that. Okay? So I only have this trace up here so that you can see how the output of this preamp, as it changes, will affect the comparison of the two signals. So if we put this, so what I'm going to do is I'm going to overdrive this preamp so that it distorts. And watch what happens at the output here. Okay, and you can see now I've driven the preamp into clipping because I'm putting too much signal into the preamp. And you can see what happens down here is you get this crazy looking clipped off waveform. So really we don't need this trace up here. I'm just doing this to show you what distortion and clipping looks like on this. So if we were using this on a power amplifier, for instance, and we were checking for harmonic distortion, you would notice the distortion as soon as that signal there started coming out like that. So that's what's going on. So you can see how many different things you can find out about a device under test, measuring its input versus its output. You can also compare the left channel to the right channel. And that's what we're going to do next. So let's see how that works. Okay, here's the setup we have now. So we come out of the signal generator and we're going into this splitter here. And all this does is it just splits the mono signal into two identical signals. It's not really stereo. It's just two mono signals that are tied together through a resistor network. So these are set for 1K right now. It really doesn't matter for what we're doing, but this will be fine. It then goes into the input, or the auxiliary input of the CA-2000 down here, We come out of the output. This would be what you would normally connect your power amplifier to. And it goes into the difference amplifier. Comes out of that after it gets summed up and goes into the oscilloscope. So that's it. Simple, much simpler. And here's the thing. If both channels are identical in amplitude, phase, and everything, you should not get anything you should get a flat line on the oscilloscope. So if we move over to here, that's essentially what we have right now. If you look at it, is a flat line. And I have this pretty sensitive right now, but if I turn the, let's see here, I'll go here and here. If I turn the balance pot, you can kind of see me turning it here. Watch what happens to the scope. That's to the right, that's to the left. So if one channel is stronger than the other, you get a difference between these two inputs, and as a result, it shows up on the scope. So this is a really good test because let's say one channel is out of phase with the other. For instance, let's say one channel has a lagging phase compared to the other channel. You would see that and you would not be able to remove that from there. And you can look right here, if I turn this up to full gain, there is ever so slightly a little bit of phase difference because I can't null this out. You can see I can turn it. Yeah, I guess I can. See, I didn't have it zeroed out. There, now it's nulled out totally. Okay, that's my bad. So you have to kind of check this and make sure it's nulled out. Okay, let me go back up here. So again, if I turn the balance control, you can see how crazy. See, I have this really sensitive right now. This is, you're looking at about 200 millivolts per division. And you can see how quickly just a little bit of imbalance gives you a crazy output, right? I can crank this down here, but yeah, and it goes right into clipping. See that? Because it way overdrives everything. So there you go. So I'll turn this down. It won't go into clipping when I don't have that gain set. There you go. So, all right. Now, next thing I want to do is I want to check the tone control. Again, we're putting a 1 kilohertz tone in there. And if I turn the tone control on, so I rotate this tone control knob, I shouldn't see anything because it should, again, affect both channels in the same way. And if I turn the mid-range, I'm turning it up and down. Let's make this way more sensitive. And you could see when I turn that the whole way up, if I turn the mid-range all the way up as far as it'll go, what happens is you get that distortion. That is because the treble, even one click away, the treble, the roll-off of the treble frequency is different between the left and right channels. You're seeing that in there. Now if I turn it down so it doesn't crank it up, that goes away. Now if I go to the, I'm sorry, I was on the mid-range. Now if I go to the treble control and I turn that, it doesn't have any effect. You can see it attenuates it a little bit. So now let's set this down here. I'm going to turn the 2 kilohertz turnover for the treble. I'm then going to go up to the scope. I'm going to change that to 2 kilohertz, right? And then I'm going to put you back on the scope. And again, I should not have any difference, but if you look, I do. So this is just turning that 2 kilohertz up and down, and you can see how it does change the amplitude. But I should have, both channels should be the same. In other words, you should still have a flat line. Let's see if I can adjust this. There, it's nulled out right there. That's the null point. And you notice I had to readjust the null point. So it tells me that one channel is outputting a little bit more than the other, meaning the treble control is not linear between left and right channel. Now again, I'm on, it's very sensitive how it's set right now, but nonetheless, and you can see if I turn either one of those left or right balance, it goes crazy. But if I turn the tone control off, it unnulls, and you can see I can null it right out. See there? But if I turn the tone control on, you can see what happens. And the more I adjust this, they get different. So what that means is my treble control is not tracking between the left and right channel. Now, boy, is that going to cause the comments to go crazy, isn't it? Well, if you did this test on the majority of analog gear like this with tone controls, you'll find this, especially when you're using this type of test equipment. This is not something you're going to hear with your ears, a difference between the left and right channel. At least I don't think most people would, but just know that it's there. If we go down to a lower frequency, so let's take it down to, let's say, let's go into the base frequency, 150 hertz. All right, 150 hertz. And I got to change my time scale a little bit. And if I go off, you can see it's flat. But if I turn the tone control back on, and you can see my hand turning the tone control, I go down to the 150, you can see there is a very distinct difference between the left and right channel. And you see if I turn the bass down and I turn the bass up, the difference between left and right channel gets more pronounced than when you're flat. Now, in a perfect world, when you set these tone controls all to flat, they should have no influence whatsoever over that signal. But you can see they do. And this is even at this is the receiver that's been recapped. So the capacitors, while they may have helped a little bit, you still have all these things in there like the transistors, the controls themselves, the contacts, which were cleaned properly and deoxed or whatever you do. The potentiometer could be, a little different, although these don't have potentiometers for the tone control. They have switches. They're actually stepped attenuators. And you can see, and if I go back to turning this down to flat, defeat, so no tone control, look what happens. I turn it on to tone control. All of a sudden, one channel is more than the other. And I can find that out by rotating this, the null point. So you can see the right channel seems to have less roll-off than the left, and that's what's causing that. Now if I go back to tone defeat, there you go. Interesting. Okay, so I'm going to end this video right here because I think I confused all of you enough. I'm very pleased with the way this experiment went. Again, this is an experiment. This circuit has been around for a long time. Don't think of this as some kind of invention I came up with. It's not. And people have been doing this type of testing for years. It's just something I've never tried before. And I can see the value in having that. Am I going to test everything I ever put on my bench with this? No. But I can see how this would be a good way to evaluate something. This is a fantastic preamp. I mean, by all rights, if I hook this up to an amp right now, I bet you would love the sound of it. But even the tiniest little changes will show up when you have a difference amplifier like this. Any difference between the two channels and it will show up. So anyway, and not only can you compare left to right, but you can compare input to output. You can compare the input of a preamp to the output of the preamp, input of the preamp to the output of the power amp. All kinds of ways you can test this. And once you learn how the waveform is affected and what it means, you can detect distortion, you can detect phase differences, you can detect amplitude differences, everything. Makes it really, gives you a real visual representation of what's going on inside the amplifier. Again, it's real easy to say I put these capacitors in and it opened the sound stage and it makes it sound this, this and that and all these descriptive words, but that doesn't really tell you what's going on electronically to make that happen. I like things that give you a definitive answer that you can see visually when things happen. So anyway, I hope this was an interesting video. If you like this and you want me to do a second part to this, I will take the other preamp and stack it on top of this one, and we'll compare one to the other to see if there's any differences that way. So let me know what you think. Until then, I wish you all peace, joy, happiness, and good health in your lives. I thank you all for the wonderful comments and everything. And hopefully we can get this thing finished and get on to the CA-2000 power amplifier also. So let me know your thoughts, and we'll be back soon. Take care, everybody. Bye-bye.